Yeah, okay. Okay, so hello everyone. So this is a start of a new seminar series called Chaotic Seminar Series. And in this seminar series, we'll be having speakers who will basically give talks on topics related to chaos. And so for this, we have this is the first talk of this seminar series. And today's talk is by Alex, who is a PhD student at Trento Institute of Fundamental Physics and Applications at University of Trento. And today he will be giving the talk on the topic which is from single particle to many body chaos in Yukawa-SYK. So without further uh, um, uh, I think most of the people have joined. So let me give the platform to Alex. And yeah, Alex, welcome to the seminar, and you can start now.
Yes, okay. Thanks a lot, Beskar, and thank you for giving me the opportunity to present some of the work that we've been doing here in Trento, and also like very much this initiative of doing this chaotic seminars. So I'm looking forward to what you guys have in store about other talks. But okay, so indeed, as you said, Beskar, I will talk about this work that we've been doing under the title of From Single Particle to Many Body Chaos in the Yukawa-SYK model. But before I start, I want to first take a step back a bit and discuss this notion of holographic quantum matter a bit in general, which plays sort of a central role in the work that we're doing in Trento. And it's okay. I'm already flashing here a bit this very famous model for holographic quantum matter, which maybe some of you already know as the SYK model, which I'll come back to this in more detail. But just to give you a brief preview, it's just this model of all randomly interacting fermions. And these last couple of years, this has gained a lot of attention from various different communities. Originally, it came from more a string theory, the holographic community, and indeed, hence shows also a lot of connections with black holes. Sorry, before I forget, by the way, guys, if any of you have questions during the talk or something, feel free to interrupt me and ask. I mean, I prefer to explain immediately something again if something was unclear. Instead of you guys having to wait until the end and maybe not following. Okay, so let me continue. So on one hand, you have this nice connection to cosmology and quantum gravity and black holes. Um, but there is also a big part of the condensed matter community that is interested in these models. Because as it turns out, these are phenomenological models for strange metals and non-Fermi liquid behavior, which are things that tend to happen, are properties of high temperatures superconductors that show this strange metal phase. So yeah. And then lastly, and this ties closer together to the work that we have been doing here in Trento, these models are also very interesting for quantum technologies and simulations and for quantum chaos and information in general. And so today I will discuss mostly these bottom two panels and in big part the bottom left, the quantum chaos. This is a quantum chaos seminar. Um, but yeah, this I just want to emphasize that this work that we are doing is very much at the intersection between these two main panels. But nonetheless, I think it's nice to give a sort of brief overview of all these different sections, and this can really show you why these SYK models and this holographic quantum matter are so eclectic in a sense and pop up in the literature of various disciplines of physics. So okay, let me try to explain holography in a nutshell. I'm by no means an expert on this. So I'll give a very layman understanding, but at the fundamental level, the duality breaks down to these two partition functions being the same, in the sense that on one side you have a quantum field theory, and on the other side you have a gravity theory, and it turns out that they describe similar or same physics because they show the same partition function. So, okay, what do I mean by that in more detail? It's in the field theory side, you have some source terms given by this hi, which can, for example, be particle densities or density currents, and these can couple to some operators OI. While at the other hand, at the gravity side, these fields are fixed on the boundaries and on the boundary of your gravitational theory, and these define the gravity theory throughout your entire bulk. So in a sense, what I'm saying, or what holography is saying, is that essentially this means that if you have a gravity theory that is defined by a field theory on the boundary, you know what's going on, right? So if you know what's going on the boundary, you know exactly what is going on throughout the gravity theory in the bulk. And hence the name holographic quantum matter, right? Because if you have a field theory that lives on this boundary, it's a bit like a hologram, where you have your fundamental information somehow stored, encoded in this boundary theory, and this then defines a sort of an emergent gravitational theory in the bulk of your space-time. And so hence this connection with cosmology and quantum gravity and black holes. And now, again, here this SYK model pops up. I'll get into much more detail about this later, but around 2015, Kitaev realized that this very simple model of where you just have some n different interacting, n fermions. They can be complex or Majorana fermions. If you make them randomly interacting all to all with each other, it turns out that this is a very simple example of this holographic quantum matter. And more precisely, if you make this n, so this number of fermions, if you make them go to infinity, in this limit, this is dual to a gravitational theory known as Jacobi-Teitelbaum gravity, which is a two-dimensional theory of gravity. And hence this connection. And okay, I'll get into some of these topics in more detail. But what these models typically show is this maximal chaos, these are fastest scramblers, etc. Now, this connection, in a sense, with black holes has also some immediate physical consequences, because it is known that if you perturb a black hole or you throw some information in it, this perturbation, it will relax extremely quickly to equilibrium. And it will do so at a sort of time scale that is proportional to the inverse of the temperature. And now on the field theory side, what does this mean is that if you will perturb your theory, this information gets scrambled very quickly along the entire system, among all the degrees of freedom of your system, again in this time scale as 1 over the temperature. And very interesting result that Malgasena, Schenker, and Stanford proved was that there is a sort of bound on this scrambler. So this influence of chaos, I'm already anticipating some concepts that I'll introduce better later, but they cannot develop faster than exponentially with this Lyapunov exponents given by this bound. And hence this has very deep connections, as I mentioned, with quantum chaos and quantum information. Okay, I already mentioned that this SYK model and black holes, they saturate this bound. But anyway, I find it interesting that if you would consider naively some theorems, some theories with quasiparticles, you immediately see that this cannot work. Because if you have a theory with quasiparticles with a gap of mass m, then this would take exponentially long. And even if for gapless systems, this would go as 1 over temperature squared, which is much bigger at low temperatures than this 1 over T. So this is kind of an indication that this holographic quantum matter must be a system without any quasiparticles. And interestingly, this is exactly tying back to this condensed matter interest. This is exactly what happens in this strange metal phase, where this phase can not be described by any quasiparticles, and hence this is why this SYK is also so interested for people from the condensed matter community, where it's really a toy model for this non-Fermi liquid behavior. It's okay. I mean, I hope I kind of convince you of this interest of this holographic quantum matter and the SYK model in general. And so let's try to find it, right? Because in a sense, these models, they do not really naturally occur in nature. So that's why people and also we in Trento with some other collaborators are looking towards a sort of cavity QED quantum simulation of this SYK model, where the main idea is that you put some cloud of atoms into a cavity and effectively you get out an SYK-like interaction. And okay, here I just want to give you the main gist, the main idea of how this works. So if you are not following all these details now, that's okay. I just hope that I can convince you of the main idea that you get out this effective interaction that looks like an SYK model. Sorry. So what's the basic idea? The proposal is based on some multi-mode cavity. So what do? You have a cavity sitting there with some cavity photons in your cavity. And in the middle, you in a sort of pancake structure, or you fix some atoms, some fermionic atoms. And okay, the spectrum of this atom can be either in the ground state, or you can be in the excited state into various different modes. And you can go to these modes by absorbing cavity photons with different detunings. So yeah, depending on which mode you're looking at. And okay, in second quantization, the Hamiltonian of this process or this thing that is happening inside the cavity is given by this Hamiltonian, where, as I said, you can go from a ground state to the excited state by absorbing a photon with cavity mode M. And of course, also the inverse process is happening. And as I mentioned, you have some sort of cavity detuning because you will add an external drive, a coherent laser beam from the side. This simply to boost interactions. And so everything is measured with respect to this detuning. And so indeed, you have to add also this extra term at the effect of the classical drive, which also can allow your atoms to go either from the ground state to the excited state and back. But okay, I put the Hamiltonian for completeness, but I think it's much more intuitive to think of this in terms of some Feynman diagrams. So what this process is just saying is that, look, you can have an excited state, which by emitting a cavity photon can decay back to your ground states. And of course, also the Hermitian conjugate process happens. And same here with the classical drive, where your ground state atom can absorb some stuff from your classical drive and hence get excited into the excited state. So these are the two fundamental processes happening, in a sense, in the cavity. And what one can now do is effectively concoct your cavity in such a way that the resonant process is the one given here below. And then now the nice thing is that if you go to second order imperturbation theory, so you just assume that these 2D tunings are very large, you can effectively adiabatically eliminate this excited state in this process, and hence this thing collapses to a sort of 4-point interaction vertex. So what means that you have 2 fermionic states coming in and 2 coming out. So effectively, this is a sort of SYK-like interaction that they can construct. Okay, to be completely complete, they are not yet random. This is done by imposing an optical speckle pattern into the cavity. But if you're convinced, at least, that you can have this 4-point interaction vertex, I'm already very happy. So okay, that's the cavity quantum simulation side of it. But now let's move to the reason why you're here, who talk about chaos. And when people talk about chaos or quantum chaos, they typically look at 2 different, let's say, family of markers. One being spectral correlations, which is more of a late time notion of quantum chaos. and other more dynamical behavior like this out of time ordered correlators, which often are more seen as a sort of early time notion of chaos. And as I as I said, these models that I want to see, I want to explain to you, kind of the difference between integrable or single particle chaotic models and many-body quantum chaos. And for this, let's start by looking at a very simple model. This is essentially some non-interacting fermions which are hopping on the sides of a random matrix Gij. And what they take is, okay, we take this random matrix, these random variables, to have zero mean with a variance given by this value, where J is just some energy scale. And so physically, how can you think of this? You have these different fermions, and they're just, as I said, randomly hopping from one side to the other. Here I've drawn just some interaction. And this is also known as a SYK2 model, but as I said, it's just essentially some non-interacting fermions randomly hopping around. And okay, this, you might already realize this at least is a completely very easy and integrable model. On the other side, we have our very famous SYK4 model, which just extends this thing with the 2x2 body interaction. So here we have the Hamiltonian, and again, you have some independent random variables with this zero mean and variance given by this scale. And okay, let me make the remark that often people take these random variables to be Gaussian, but this is actually not very fundamentally necessary for the story that I'm going to tell. The important thing is that they are just independent random variables. And okay, typically, indeed, for all these markers that I will discuss, keep in mind that these are typically averaged over different independent realizations of disorder of this model, since we're actually considering an ensemble of different Hamiltonians. So okay, let's go ahead and start to consider first some spectral probes of chaos. And here, the main idea is actually pretty simple, is that integrable systems typically are characterized by an extensive number of symmetries, and hence they will give rise to some uncorrelated energy spectra, while chaotic systems typically exhibit very correlated spectral properties, and hence they will follow some universal behavior that follows this random matrix theory. So, okay, the first step that people often take is to say, okay, let's look at the many-body density of states, which is given here by this rho E, where the E are, okay, the various En are your various energy levels if you're from your Hamiltonian, right, from your system. And okay, here on the left, I plot some schematic overview of the density of states of what's of the SYK2 model. So you see this sort of nice Gaussian distribution of the energy. This is a histogram of the energy level, sorry. And if I zoom in at the low energy band, I see that down at the tail of the distribution, the levels they are spaced as 1/n, right? So, as I said, in the tail at the bottom of the band, the energy levels, they become sparser and sparser, and the spacing goes as 1/n. And okay, this, in a sense, it's essentially an indication, if you want, of the quasi-particle nature of the system, if I would allow for weak interactions, right? Because this 1/n is what one would expect simply from Fermi liquid theory. So again, as I mentioned, this is the typical scenario of integrable systems. However, I want to make a small side note that I'm talking here about the many-body density of states. If, however, you would go into the single particle representation, the spectrum of this SYK2 model will follow this famous Wigner semicircle distribution. Due to, because there essentially, if you're doing a diagonalization, you're diagonalizing just a random matrix, right? This random Gij matrix that I was talking about. So of course, in your single particle representation, you will get this semicircle back. And hence, this is for me already a first indication or very intuitive way to think why people call this SYK2 model a single particle chaotic. All right, because at the single particle level, it does show this chaotic behavior. It does follow this random matrix structure. But of course, at the many body level, if you consider your Fock space representation, if you want, of course, this thing is just integrable. Okay, on the other hand, if you now look at the SYK4 spectra, it looks slightly different. And more importantly, if you zoom in again at the tail of the distribution there, you will see that this spectra is exponentially dense in the tails, right? So there the level spacing goes down as e to the minus some proportionality factor alpha n. And so, of course, this is then also an indication that here this quasi-particle nature of your system breaks down. So, okay, this is an first nice view on chaos on the spectral statistics, but it's a very crude marker, especially if you want to do some numerical work, distinguishing this. Did we have a message? Okay, I don't know. Distinguishing these various levels becomes increasingly difficult. That's why people typically often also look at some gap ratio distributions, or yeah, here I'm actually just plotting the level spacing distributions. And what do I mean by that is that, look, if you would order your you have an Hamiltonian, you do a diagonalization of it and you get the eigen energies from it and you order them. If you look at the spacing between consequent energy levels, you see that they behave vastly different for integrable and for chaotic systems. As I mentioned, this integrable system have a lot of symmetries and have an uncorrelated spectrum, so they typically will follow this Poissonian distribution. While on the other hand, chaotic systems will follow one of these curves that I've plotted here. And importantly, they show this effect of level repulsion, which is nothing else than the energy levels not wanting to sit together. So they really repel each other. And this is yeah, a famous conjecture in quantum chaos, known as the BGS conjecture, that states if your spectral statistics, or more precisely, your spacing distributions follows the one as predicted by random matrix theory, given here in the solid lines, then people typically consider your system to be chaotic. This is one of the basic conjectures in the field of quantum chaos. Clear until now? I hope so. Now, one downside of the markers I've discussed up until now is that they're very local. Local in the sense that they are just probing nearest neighbors, or next to nearest neighbors, if you want, correlations in your energy spectrum. And that's why people typically go look at the spectral form factor, which shows a much more long-range correlations of the system. And okay, the spectral form factor, I've written it down here, and essentially it's just an analytical, it's the square of the analytically continued partition function in real time. And the nice thing of the spectral form factor is that it has some very distinct structure, at least for chaotic systems. Here I plot the spectral form factor for the complex SYK model for various realizations. And so you see that after a while, very nice structure seems to emerge. First of all, you have some slope, some decaying part, which is very system specific. But importantly, at late enough times, you see this development of this linear ramp. So first you have a dip, and then a ramp, and then this plateau structure, which follows the universal behavior as known by random matrix theory. So typically, if you look at the spectral form factor of your system and you see this nice dip ramp plateau structure, I guess you can be pretty sure that it's a chaotic system. While at the other hand, if you have an integrable system, it lacks this structure due to all the symmetries that it has. So it cannot really create this ramp, because this ramp is a manifestation of some long-range level repulsion. So if you want, it's a sort of spectral rigidity of an extended bandwidth of energies in your system, and hence you will increase before then hitting a plateau. Again, a side note for this YK2 model, which, as I mentioned, it is integrable, but anyway, single particle chaotic. And this can be seen also in the spectral form factor, where this random matrix structure of your single particle Hamiltonian, so this JIJ coupling, persists often in the form of an exponential ramp. So there, you will not have a linear ramp, you will not have this nice structure, but anyway, for SYK2 models, you will see some increase in time in your spectral form factor. Okay.
Okay, Alex, one query,
Yes.
like when
Go ahead.
we are like for the spectral form factor, like during level statistics, basically we get all the energy eigenvalues and do the diagonalization procedure. For a spectral form factor, what are the procedures that we like go by? We first find the eigenvalues, and then can you just give a brief overview of like what steps do we follow during this SFF procedure?
Yeah, so typically in numerical work, at least, it all boils down to this formula. So you have an Hamiltonian, which indeed, as you said, you will go through exact diagonalization. Then this will give you your eigenvalues, and then you just compute this thing in a sense, and for various times on a logarithmic time, and then you will see this behavior emerging. Normally, yes. At least in a simple way, this is the procedure. That's what it boils down to. Yes.
Okay. So fundamentally, what's the difference between the two procedures, the level statistics and this spectral form factor? Are they representing the same phenomena, or are they telling something else that the level statistics are missing?
Yeah. So as I said, these level statistics, they are, especially here, they're just kind of probing some local. Local is maybe not the right word, but to me it looks like a much more local notion of chaos, because you're just probing this level repulsion in a sense, like how much do my energy levels not want to be on top of each other. While here in the spectral form factor, this is a much more spread out. It's more it's probing long range correlations in your system, while here you're just probing short range correlations.
Okay.
Is that clear?
Okay. Okay. Yeah. Clear. Thank you.
So it's a much broader notion of chaos, if you want.
Okay. Okay.
Okay.
Can you, I have a question.
Go ahead.
Yeah, can you just briefly explain what are you averaging over? What is the bar? Because
The bar,
I think that's
yes.
Yeah.
So this is, maybe I was quick here. Is these different realizations of this? Let's see it here. Here, this GIJ, it's a random matrix, right? So what you would do is you generate a Hamiltonian with some random inputs. Then you generate another one and another one. I mean, this you average over the various random matrices.
So it's an ensemble of SYK2
exactly.
or SYK4 models.
Exactly. These SYK models are typically always an ensemble of Hamiltonians.
Thanks.
Yes. No worries. Thanks for the question. Okay. If no other questions, then can move to the last marker of chaos, which maybe is the most intuitive one, at least to me, because this has maybe a nicer analog in classical chaos. And this is a dynamical probe, which is known as this out of time ordered correlations. And what they do, they track the growth of initially local perturbations, probing the operator spreading and information scrambling throughout your system. But this is nicely shown here on the right in these two figures. So in the left panel, for example, at time t0, you have these two operators A and B, and you locally perturb this operator B, right? And okay, at this initial time, they will essentially commute because they are locally separated, these two operators. But if we then now look at the right figure, see that after some time, this operator in this perturbation in B has evolved, right? And this red blob has spread out over space and now is overlapping with this operator A. And so this spreading, as I said, represents how a local initial perturbation affects more and more degrees of freedom in your system. And typically, this can be quantified by this commutator squared, right? And so in chaotic systems, this commutator, you will see, so the spreading of information, of perturbations, will be exponentially quick, right? If you want, this is a sort of quantum analog of the butterfly effect. And so, as I mentioned, this chaotic system, they scramble or spread out this information exponentially fast. And okay, equivalently, if you would work out this commutator squared, you will see one of the terms that pops out is this out of time ordered correlator function given by this ft. And yeah, this is just equivalent states either will exponentially decay. And again, here this bound on chaos pops up because the fastest way that this can decay is through this, it's bounded by this Lyapunov exponent given by this 2 pi p over h bar. So typically, if you look at a chaotic system and you compute this out of time ordered correlator functions, you will see an exponential decay at early times. And interestingly, if you go to large n, this SYK4 model is known to saturate this bound in the strong coupling limit. So if you take this beta j to be very, very big. And not incidentally, this is just the same as for black holes. Black holes are known to be maximally chaotic and the fastest scramblers in nature. This ties back to what I said in the beginning, where if you perturb a black hole or you throw in some information, it will scramble this information as fast as possible, as fast as allowed by quantum mechanics. And on the other hand, integrable systems, often they do not show any exponential decay, or more importantly, also sometimes they saturate to non-zero values depending on the symmetries. And this is a behavior that happens at finite system sizes, but this is due to a lack of full scrambling in your system. So that's the difference between integrable and chaotic systems at the level of the dynamical chaos or the early time chaos. Now, okay, finally, let's come to this Yukawa-SYK model, and I will now try to convince you that this is a very natural and a very tunable framework that can interpolate between the single particle chaos that I mentioned of the SYK2 model, so an integrable system, and the many-body chaos of the SYK4 model. And this, I mean, for the literature, it can be kind of interesting because the transition or crossover between single particle chaotic models and many-body chaotic models is not very well understood, at least as far as I know. So from that perspective, at least for the chaos community, I think this Yukawa-SYK model can be an interesting framework to study this interpolation. So, okay, how does the Yukawa-SYK model look like? It's very similar to the SYK model we had before, only that now we throw in some scalar bosonic degrees of freedom given by this phi k, or here in red. And so effectively what is happening, you still have your fermions in blue sitting here, but now the interaction or the hopping between these fermions is sort of mediated by the red bosons sitting in your system, right? So, and the bosons have a mass of omega 0. And as I mentioned, they interact through a Yukawa-like interaction, hence the name Yukawa-SYK model. Again, now you have here a random interaction sitting. Now it's only in through 3 indices instead of 2 or 4. And again, here they are independent random numbers with the 0 mean and a variance given by this energy scale G. And okay, here typically, at least what people often do in the literature and what we also did in our work is we work in the half filling sector, so we can ignore this chemical potential. And what we then also did is we expressed this Hamiltonian in terms of creation and annihilation operators, bringing it to the following form. Moreover, we then have to impose, because we want to do some numerics on this thing. And sadly, the introduction of these bosons, they make your Hilbert space infinite, right? So you are forced to impose some occupancy cutoff and B on your bosons. In our work, the results I will show will be mostly for cutoff 1, but I've also checked some other cutoffs. And I will now try to convince you that taking this Hamiltonian, you can tune between SYK2 and 4 by playing around with the 2 natural parameters that are in this model, right? So you have on the one hand, your boson mass, the omega 0, and your coupling strength G. And so by tuning the dimensionless ratio of both, you can interpolate between both. But before I show you some results, let me actually remind you of this cavity implementation that we were working on, because this is actually originally how we kind of came up with studying and were motivated to study this model. Because, as I said before, you have these 2 microscopic interactions, these 2 elementary interactions, and then you adiabatically eliminate and you find the SYK4 interaction. But in a sense, we realized, look, but what if we just go 1 order in perturbation theory less? So what does this mean is, like, we do not assume this delta M to be large, and we take what is happening in the cavity in a sense at face value. So we keep this interaction vertex, and okay, naively you can immediately see this is exactly a Yukawa-like interaction. You have here these 2 fermions that interact through this cavity photon field. And so the interaction that you have in the optical cavity is a sort of Yukawa-SYK interaction, but with spinless fermions. Okay, I mentioned this because typically in the literature, people study more the spinful version. And so you have this tunable knob of G over delta M, or in our numerics, G over omega 0. So this is just as a side note, as an intermezzo, to keep in mind that this Yukawa-SYK model is also very interesting, at least in my opinion, from a cavity QED point of view. Okay, let's now look at some of these chaos markers that I was mentioning before. Here I plot the density of states and gap ratio distribution. And if we first focus here on the left side of the plot, so in the regime where you have a very small boson mass or very strong coupling regime, you see that you have you retrieve this nicely Gaussian distribution that we're used to from the SYK2, and also some Poissonian level statistics. And in a sense, this is not so surprising, because if you go into this strong coupling limit, so where omega 0 over G tends to 0, the boson mass term in your Hamiltonian becomes in a sense negligible compared to the interaction term. And hence you can consider the system to be dominated by a quadratic fermion theory with the hopping strengths. They're simply just renormalized by your bosons, right? And so hence we nicely see this reflected in the density of states, showing this Gaussian behavior, and the gap ratio distribution showing the Poissonian statistics. Now, as we move to bigger values of omega 0, you see that, okay, the density of states remains slightly Gaussian, but the gap ratio very quickly moves towards the GOE prediction. And eventually, if you keep tuning this boson mass enough and enough, you see that your density of states will sort of start splitting, right? So at this point and further onwards, the effect of the boson mass becomes so strong, becomes so important that distinct peaks start to develop in your density of states for each boson occupation sector. And eventually, they separate into well-separated clusters. Now, we will see in a second that although, yes, this global structure seems to be a bit broken because of these bosons, if you would restrict yourself to one specific cluster here in this density of states, you see that this chaotic behavior will persist. It's okay. This is a first overview, sort of phase diagram, if you want, of this Yukawa-SYK model. I know it can move, but as I said, let's also look at some maybe other markers of chaos. So, for example, here we computed and plotted the spectral form factor at infinite temperature. So we took beta 0 okay, here we took and so 8 complex fermions and 4 bosonic modes with cutoff 1. And of course, as I mentioned, we average them over different disorder realizations. And here you nicely see this behavior, no? So at first, here we're restricting to very small values of omega 0. And you see that you have this very slope and decaying behavior with then eventually this dip. And then you have an increase, which is clearly super linear. It's bigger than linear. And then this plateau value, indicative of the single particle chaotic SYK2 behavior. And here we plot this 2n is the it's this dashed line. It marks the SYK2 plateau time, and this TH is the Heisenberg time. Okay, these are just values of where one expects the plateau to start and the ramp to start. So here clearly there is no ramp. But as you start tuning and increasing the mass, this omega 0, you see that little by little these curves start to go down, and you start to develop some spectral rigidity, which is reflected in the linear ramp that you start to develop, right? So this is a nice indication that, okay, here we have some single particle chaotic behavior, but as we tune and increase the boson mass, we move more and more towards the chaotic and many-body chaotic sector. Now, before I show you the other side of the spectral form factor, I want to jump to the autox in this regime. So here we plotted the autox for this f of t for the following operators. So here we took a and b just to be this sort of number operators. This is chosen for numerical convenience. And we see the following behavior. So in the red dashed curve, we have the autoc for the SYK2 model. Again, for the same number of fermions as the Yukawa-SYK model that we're considering in this figure. So you see that after some initial decay up to the scrambling time, the autoc saturates to this non-zero value, right? To remember, this was this very characteristic behavior of an integrable system that are not fully scrambling at finite system sizes. And the blue curves, they show the autocs for the Yukawa-SYK model. And you see that for very small enough omega 0, these curves, they very, very nicely follow the early time decay of the SYK2 and even saturate at the same intermediate plateau value. However, if you wait long enough, or if you take the boson mass high enough, you see that at sufficiently large times, you observe some omega-dependent deviation from this SYK2 plateau. And so this is very reminiscent of some sort of pre-thermal or pre-scrambling behavior, right? So you have these autocs, they decay, they follow the SYK2 model, and they show some robustness. They don't fully scramble, but if you then wait long enough, eventually they do decay and become many-body chaotic and decay to zero. The fact that here they are not showing to be completely zero are just some finite size effects. And there is actually a nice explanation, nice physical explanation for this behavior, namely that in the limit where this omega zero is negligible in your Yukawa-SYK Hamiltonian, so for very small omega zero, you can see your Hamiltonian as to that you can diagonalize it over different bosonic sectors, right? And in that regime, it's in a sense then governed by simply quadratic fermionic Hamiltonians, right? Which each have some sort of conserved charges given by the occupation number of the fermionic modes. So the way I see it is that since omega zero is so small, as you can think intuitively, or at least, as your Yukawa-SYK Hamiltonian having some different blocks of some different sectors of SYK2-like models. And since for small omega zero, these symmetries within each of these sectors are only weakly broken, the scrambling is constrained within each of this fixed sector. But as you increase omega zero, so if you move to bigger values of the boson mass, this becomes more and more significant. You will start to break these quasi-symmetries, and you will allow for transitions between these different symmetry sectors, which as consequence will allow this model to explore the full Hilbert space, and hence you will decay towards zero. Now, a neat thing that one can do analytically is that the time scale, so the time scale at which these autocs deviate from their pre-thermal, let's call it pre-thermal plateau, this can be computed nicely from perturbation theory. So what you do is, since omega zero is small, you consider this kinetic term as a perturbative part on top of this Yukawa interaction, and then one can do a Magnus expansion from it, and you see that the leading time scale for this interaction goes as g over omega 0 to the 5 over 2. And this is exactly what this inset figure showed. There we have rescaled the time by this time scale, and so you see that the curves nicely overlap, especially in their decay part, indicating indeed this time scale at which the autocs decay from the SYK2 part. Note also that this last curve actually does not collapse, which is indicative of the fact that this omega 0 is already much, much too big to be considered in this perturbation theory. And indeed, you're already much outside what one would call the SYK2 regime. So yeah, this is a result I actually like very much. It's kind of shows also the power of simple perturbation theory and how nicely it can predict and agree with the numerics that we did. Okay, if no questions on that part, then let's move to the other side, to the more SYK4-like regime. So now we are considering autocs for very large values of omega 0. And here I plot some of these autocs for omega, for boson mass 3 and 10. And okay, you see a couple of differences. First of all, they seem to moderately saturate to 0. And moreover, the solid lines show some oscillating behavior. The dashed lines, on the other hand, are the corresponding autocs if I would restrict myself to the lowest energy peak. Because remember that in this regime, our density of states is very clustered, right? So what this thing is showing you that is that as you increase the boson mass, so if you compare the blue curves for 10 to the red ones for 3, you see that the low energy peak becomes a better and better approximation for the full spectrum. And that this, and moreover, that these oscillations get more and more attenuated, right? And this is, in a sense, can also be seen from this panel B, where we again did a rescaling of the axes by omega 3 and omega, and we show a nice collapse of this different value of the boson masses, indicating that indeed these things go down and the autocs start to oscillate quicker and quicker. But so now let's then now consider, as I mentioned, the auto, but just restricting. So we do just a calculation for the low energy peaks, and here this is given. The result of this is given in this panel where we plot the autocs for different values of omega 0, and here you nicely see the behavior what we want to see, right? So by increasing this omega 0, we we approach the early time decay of the SYK4 better and better and better, and also you will saturate to 0 at late times. So this is very much the expected behavior, at least from the auto point of view, that one would expect for a chaotic model that is fully scrambling. So yeah, this is a very nice result, and this behavior of the autocs, actually, again, we can understand them better this tendency through perturbation theory, or more precisely, this approach to SYK4, you can understand them through what is known as a Schrieffer-Wolff transformation. And what this basically is doing, it's just systematically integrating out your bosonic degrees of freedom, because as I was mentioning, in this regime, your bosons are oscillating so fast that you can eliminate them. And if you go through the calculation there, it's pretty straightforward calculation, you will get an effective Hamiltonian that looks something like this. And so here you nicely recognize this SYK4-like interaction, or at least these 4 fermions interacting with a coupling that is slightly different, but the effective coupling strength is given by this G squared over omega 0 squared. And so as I was saying, this larger omega 0, the bigger you make it, the better this transformation actually becomes, indicating that this approximation becomes more accurate, which physically is also what you could expect, because if these bosonic degrees, they start oscillating so fast that effectively they become frozen, and such that each energy peak in the density of states was mostly dominated by purely fermionic interactions. And hence why we see this emergent SYK4 behavior when restricting to a specific peak. But okay, then now, as promised, let me go back to the spectral form factor in this regime. And here I plot the spectral form factor for various values of increasing boson modes, M. This is for a fixed large value of omega 0 of 10. And what you see is that the more you increase M, the better it will start to approach the red SYK4 value. And this is also, again, something we can understand by looking at this effective Hamiltonian we got from integrating out our bosonic degrees of freedom, because this interaction, in a sense, this rank of the interaction of this 4 fermion interaction increases with the number of bosonic modes, right? And hence you will start to develop this ramp. And the problem is that if you take your M not big enough, the rank of this interaction is much too low to reproduce effective SYK4 behavior. Okay, let me give, just as a small side note, the discrepancy that one sees here in the early slope, early decay, is mostly due to this normal ordering fact, because if you want to retrieve an exact SYK4, you would have C dagger, C dagger. Well, here this is not the case. When you normal order, you get an additional term, which does become negligible in the large NM limits. So in the thermodynamic limit, this is negligible, but at finite system sizes, as you see the effect of this. But okay, I think with that, I can come to the conclusion of my talk. So just to give you a brief summary of what we did, is we did a numerical study through exact diagonalization of this spinless version of the Yukawa-SYK model. And I hope that I was able to convince you by showing these various results of the different chaos markers that this is a system that can naturally interpolate between single particle and many body chaos by tuning this boson mass or this omega 0 and the coupling strength. And what did we see? That, okay, in the small omega regime, you effectively can retrieve some SYK2-like behavior. showing integrable dynamics with a superlinear ramp in the spectral form factor and these pre-thermal plateaus up to long times with then a sort of secondary scrambling process. And on the other hand, in the large omega zero regime, the dynamics get increasingly dominated by these lowest energy bands in the spectrum. And we see an emergent SYK4-like behavior reminiscent of many body chaos. And okay, lastly, we also this work, you can see it in a sort of twofold way, because this numerics, we also hope that it can provide a sort of benchmark for an implementation of this Yukawa-SYK model on quantum simulators based on ultra-cold atoms in an optical cavity, where I hope that I was able to convince you that this Yukawa-SYK model is a sort of interaction, or this Yukawa interaction, something that naturally occurs in this cavity QED setups. So okay, then I just want to finish my talk here and thank you for your attention and also already your nice questions. And before I leave, let me also thank my collaborators, especially also David, who worked a lot on this project, and the two postdocs, Samik and Andrea, and also the Professor Philip Hawken. And okay, last thing before I open the floor to other questions, I want to make some shameless publicity for a workshop that we are organizing here in Trento called Quantum Science Generation. It's a very nice workshop, I think, for young and early researchers, early career researchers that are working on anything quantum technology related. And we really try to bring together people from both the academic world and industry. So if you're free and want to come, please feel free to reach out or register. I think you can still register until this Sunday, but okay. With that, I thank you for your time and attention. And if there are any questions, please go ahead.
Okay, so thanks a lot, Alex, for this wonderful talk. And now let me open the platform for any questions. So yeah, any questions from anyone? Okay, so I had one question, like regarding this. So basically, in your Yukawa-SYK, you are basically introducing the bosons in the system, and the tuning the bosonic mass is taking you from SYK to SYK4. Is that the whole like thing in the like this bosonic mass is basically tuning the bosonic mass will take you from one side to the.
Yes, exactly. It's either it's kind of the interplay because of the bosonic mass and the coupling strength, right? Because if you look at your Yukawa-SYK Hamiltonian, these are the two energy scales, this omega zero and this G, that are there. And so indeed, by playing with these two inbuilt parameters, you can tune between some SYK2-like behavior and a regime that looks very much like SYK4, yes.
Okay. And normally, like as you told in the introduction, like SYK models sometimes have this holographic description. Like in the dual side, you will have some, like for example, there is a JT gravity dual to one SYK. So till now, till the research has been continuing, do the researchers have any idea like what can be the dual of this Yukawa-SYK interaction thing? Like, is there any gravity side, like any information on the holographic from using the holographic dictionary we can use and interpolate between the two?
Yes. So there, I mean, this is known. There has been some work on this by, I think, Esterlis and then also Schmalian and Inkov also, where they indeed study the holographic dual of this Yukawa-SYK. And the nice thing is that it actually gives rise to some holographic superconductors. For this, you need a slightly different version because you need the spins on your fermions, as you might have imagined. And crucially, also you need the coupling constant here to be real. So coming from a GOE instead of the GUE. And so this is dual. I don't know the gravitational theories by heart, but yeah, there are some I think what was it? It's some Einstein Maxwell ADS theory, which I think also close to some of the solutions that give this holographic superconductor. And for example, I think this, if I remember correctly, but I would have to double check it, that these scalar bosonic degrees of freedom that you introduce, they will become kind of the order parameter of your superconductor in the gravitational bulk.
Okay. And this chemical potential, like the thing that you have crossed, like
Yeah.
if we include it also in the main Yukawa-SYK, what changes will we expect that can happen in the results?
Okay. I think I've not fully checked it, but I mean, I'm pretty sure. I'm convinced that nothing fundamentally would change. I think probably, I don't know, the density of states. I think it will just introduce a sort of shift that one can then anyway sort of renormalize. So I don't expect this to have any fundamental consequences.
Okay, so no fundamental consequences there.
No, except okay, but this anyway, if I'm honest, for example, in the autox, you can also calculate them analytically, and I think it is known that this half filling sector is the most chaotic one. So it might be that if you consider different filling sectors, now I think of it, if you consider different filling sectors, it might be less chaotic. But I would be surprised if this would completely kill this interpolation between something single particle and something many body chaotic like. Yeah.
Okay. Thanks, Alex. So anyone has
Yeah.
any other questions?
May I ask a question?
Yeah,
Yes.
sure.
Good.
Is there any scope to study quantum complexity in this kind of model for the operators? Temporal complexity growth of the operators? For
So,
example, Krylov complexity or holographic complexity or something.
the question is if there is some scope to it.
Yes, I mean,
my answer is yes.
yes.
It's something we have been also kind of thinking about. And yeah, it's definitely some work that I think can be done, which at one point maybe we would like to do, but yeah, and so I think it's an interesting topic to pursue for sure. Looking at Krylov complexity or also other notions of complexity, since it is an interpolation between this integrable to chaotic.
Yes. Yeah. That's right. Yeah. Thanks.
Good. Yeah, no, it's a good question. It's an idea that's been lingering in my mind also, and something that we have been slightly discussing. Yeah.
Yeah, I thought because the Krylov complexity has been proved to be an order parameter to define the integrability to chaos transition. So that's why I thought that in this kind of model, as it is tuning the single particle chaos to many body chaos, if Krylov complexity or some kind of complexity may help in understanding these things. This model, yeah. Thank you.
No, thank you for your question.
Okay, so anyone has other question? Okay. So if not, let's thanks Alex for this wonderful talk. And I would like to announce that the next talk would be on the next to next Thursday. So after like 15 days. So thank you everyone for attending. And again, thanks a lot, Alex, for this talk. And everyone, thank you.
Yes. No, thank you for inviting me, and looking forward to the other talks. Yeah. Thanks a lot.
And this recording will be uploaded on our YouTube channel, and those who are unable to join can also watch it later. And if they have questions, they can ask in the group chat, and Alex is there to answer you.
Yes.
Okay. Okay. Thank you, everyone.
Yeah.
Thanks, Alex.
Bye bye.
Okay. Bye.